right, so this video is going to be on what we call ice charts in chemistry. And this really is going to show you where some of these numbers that we've been using have been coming from. So we already talked about KEQ. And so this is how we come up with the concentration values of everything at equilibrium. So it's an acronym. ICE stands for Initial Change in Equilibrium. And we've used some of this back in stoichiometry. So this is something that we have talked about first semester, but now we're going to really use it for what it really is. So we used to do before, change, and after. So we're just changing it to how it is normally taught in chemistry, having to do with equilibrium. So it is a way to calculate the concentration of all the reactants and products before and after equilibrium. Okay, so we're going to do a couple example problems. Really, it makes more sense once you see the problems. So I'm starting with a reaction of hydrogen plus chlorine gas produces hydrochloric acid. So I'm taking 0.2 moles of hydrogen, 0.2 moles of Cl2. What is the amount of moles of H2 and Cl2 if there are 0.12 moles of HCl at equilibrium? So what we have is what we call what we call ice chart. And so after this problem, I'm not going to show you initial change in equilibrium. I'm just going to use ICE as the acronym. So initially, how much do you have of everything? So I have 0.2 moles of H2, I have 0.2 moles of Cl2, and how much HCl do I have? Well, pretty typical in an equilibrium. If I'm giving both reactants, I probably have no product. Now, please note you can start with all product and then go back and you would have no reactant. So one side will always be 0 in your ICE charts. Okay. Then change is happening. So change is always going to be whatever you're starting with is going to go down. So this side's going to be negative, and then whatever side is starting with 0 is going to be a positive. So you can't subtract from 0. This is not math class. So you have to go, I'm destroying the hydrogen and the chlorine to make the hydrochloric acid. So these numbers have to go down. And once I make the hydrochloric acid, I'm going to have it go up. This is going to correspond to the stoichiometry. Now this one is not very exciting because everything is 1-to-1 and then I make 2 of it. But this is going to be X, this is going to be X, and this is going to be 2X. So this is always determined by the stoichiometry. So always by what is the balanced chemical equation is going to be what the change is. And finally, you have reached equilibrium. Okay, so there's going to be something here in each one of these blocks. So it's not like stoichiometry where something goes to 0. That's different. Okay, now in this problem, I was given something at equilibrium. I was given hydrochloric acid is 0.12 moles of it. So I know that this is the quantity here at equilibrium. Okay, so I need to find what these are going to be. Well, I know that if this is 0.12 and it's 2x, it must mean if I take 0.12 and divide it by 2, I get 0.06. That must be my x. Okay, that must be my x. So if that's my x, I'm going to write it in here. That's 0.06 and that's 0.06. Okay, so what I'm going to do is I'm going to take 0.2 minus 0.06 and I end up with 0.14 moles for each one of them. And it just so happens in this example, I'm starting with both at the same amount and they're both 1-to-1, so they're both going to end up this way. That doesn't typically happen, but it's an easy one to kind of use as the example. So this is going to be the amount of each one of these at equilibrium. So these are going to be the values I use in my KEQ. But these are moles, okay? These are not concentration. Remember, molarity is moles over liters, okay? So in another problem here, I am going to show you something in a container that gives you the liters, okay? Now realize that in an ICE chart, you could do things in moles, but I'm going to show you the next example in molarity. Okay, so this next example, I have CH4, methane, is going to ethine and hydrogen gas. Okay, this one's a little bit more interesting because, again, things are not just 1-to-1 to 2. We have some other things taking place. Now, the additional information I'm giving you in this problem is that I'm in a 2.5 liter container. okay? And I'm starting with 0.6 moles of methane. At equilibrium, I'm given 0.078 moles of ethine are present. What are the concentrations of each one of these species at equilibrium? So here's my ice chart and here's my balanced chemical equation. So what I'm going to do is I'm going to write initially what I have. Well, the only thing I have is the methane, and that is 0.6 moles, okay? But I'm going to show you with this chart that I really want to do things in molarity because they're asking for molarity concentration. So I'm going to convert this ice chart into molarity by dividing the 0.6 moles by the liters. Okay, so that's all I'm doing there. So I'm going to take 0.6 and divide it by 2.5, and I end up with about 0.24 molarity. Okay. Like the other ice chart, these are both starting at 0 molarities. Okay, so whatever side you're starting from, the other side's going to be 0. Okay, again, I have to subtract from the reactant side and add to my product side because I cannot subtract from 0. And these are always going to be an X value. Okay, well, what number goes in front of this X? Well, it's going to be 2X because it is balanced with 2 in front of it. This is going to be X, and this is going to be 3X. All right, so at this point, this is 0.24 minus 2X. This is X, and this is 3X. All right. But in each one of these ice tables, I'm going to give you something at equilibrium. So you're going to have to go back to the problem and say, okay, what's at equilibrium? What number do I have? Well, I'm given the ethine at equilibrium. That's 0.078 moles, okay? But that's in moles. That's not concentration. So that's going to be this number here, okay? So I'm going to take 0.078 moles and divide it by the 2.5 liters, okay? And that's going to give me my concentration of ethine at equilibrium. So when I divide those two, I end up with 0.031 molarity. So that's my X, okay? So that's 0.031 molarity, all right? So H2 easily, I could just take 3 times 0.031, and we're gonna have some rounding issues here, but we don't care about that. 0.094 molarity is going to be my equilibrium. And then I gotta go over here. So this is 0.24 minus 2 times, what's my X? 0.031. So that ends up being about 0.18 molarity. Okay, so this is my molarity, this is my molarity, this is my molarity. Okay, so if I wanted to find my KEQ at this point, I would take my C2H2 over my H2 cubed, and then I would put the CH4 squared. Okay, well, these numbers I just calculated are the ones that are going to go in here. So 0.031 molarity. H2 is 0.094 molarity. And then the bottom here is 0.18 molarity squared. Okay, so that would come out to be my KEQ. Okay, so this one, let's see if I could do the numbers real here. All right, so I get a very small number to the -4th. So this KEQ is less than 1. Okay, this KEQ is less than 1. So I know my reactants are favored. So I know it stays more as methane than it does this. Now, typically what we do with this information is we show some kind of graph, okay, to show what is happening with this equilibrium. Okay, and so with this graph, I have concentration on this side, and I have time on my x-axis. So concentration is always going to be in molarity. Okay, so I have C2H2 and H2 starting at 0. Okay, so going back to the starting point, these are starting at zeros, and then I have 0.24 as my starting point for my CH4. Okay, so these are going to be graphs we just freehand. So it's going from 0.24 down to 0.18. So I'm going from 0.24 down to 0.18. Okay, so I'm going to label that as 0.18. And then my H2 is starting at 0, and it goes up to 0.094. So I'm going to go there, and that's going to be about here. So 0.094 molarity. And then C2H2 is going to start at 0 and go to 0.031. And again, these are going to be graphs that we focus on. Sometimes we'll focus on them, sometimes we won't. But with each one of these types of graphs, it kind of shows you, okay, once you have hit the plateau, you now have established equilibrium. Okay, so that's what these ICE charts are looking at in terms of finding the concentrations. And then you could take that number and find a KEQ, and you could even take the graph part.